It's a French name, but let me show you how to say my name will work fine.
Okay, I see. Well, welcome everybody. My name is Kim Hewitt. Hopefully you're aware that I'm your professor in EDUC 2110. And uh, Christopher, just to give you quick background, I know I probably gave you some background over email, but the class I teach is Issues in Education. And so we explore a variety of issues, and these students in this class they haven't yet begun their upper division education and or speech language pathology programs yet. They're sort of freshmen and sophomores a lot of the time, maybe juniors, but they have a lot of upper division coursework to work on once they've begun their program. So this is a class about exploring issues in education, and as part of the class, they do 10 hours of field experience in a setting, educational setting or other sort of social setting to learn about how people interact with each other and do social programs. And so what I've offered them and what you're part of and you're bringing to us is sort of a field experience. You're 1 hour of their field experience tonight, and they're just kind of learning about computer science education and how this is sort of a new issue again. I know it's been an issue. I know we've been doing computer science education for decades, but it's kind of in style again. And so we want to hear from someone who you've practiced it, you've lived it, you're a professional developer at Georgia State or Georgia Tech, excuse me. You're currently a computer science teacher, but I know you can probably introduce yourself. But just to let you know, guys, really quickly, I first met Mr. Michaud at the Georgia Educational Technology Conference about 8 years ago. He was a music teacher at Nebo Elementary in Paulding County, and amazingly, he had all of his music students demonstrating Lego robots at this conference, and he did a presentation that I don't think I got to go to, but he made a real impression on me, and I was able to find him again here 8 years later when I needed him. I just think that he's got a great perspective from the field of the classroom, from the K-12 school. He's taught at public schools. He's currently, I believe, in a private school, which he'll tell us more about. So he's got a lot of perspectives to bring, and I think he's got kind of that interdisciplinary spirit. What kind of music teacher does computer science? Well, he's that kind of teacher. Very quickly, I want to just tell you, make sure that I gave you a link to a survey that I'd like you to respond to. It's sort of your reflection on the experience tonight. It asks a few questions about some things you learned about in the session tonight, and then it asks you some other bigger questions that are more reflective in nature. So make sure you do that, and then you don't have to really worry about reflecting on this in your big final reflection for the class. But you can ask me more questions about that later. I sent a link to that in the Corsten email and in the outside email as well. This presentation should take about an hour, and then we have about 15 minutes at the end for questions and answers. So write your questions down, and you'll have a chance to ask them at the end. All right, I'm going to turn it over to you, Mr. Michaud.
All right, well, thank you very much, Ms. Hewitt. My name is Christopher Michaud, and I currently teach computer science and robotics. Well, actually, I teach human beings, but I teach at Merit School in Atlanta. As Dr. Hewitt has said in her introduction, I've been doing this for about 8 years. In preparing for the presentation tonight, I had to go back through, pull out a lot of things I did when I was an elementary teacher, and it just reminded me of how long I've been doing this and how long this has been around. Education. It truly comes in cycles. So I'm really pleased to meet and work with everybody tonight. Some background about myself. I majored in music in college, music education. I was pretty convinced when I was a sophomore and a freshman that I was going to be a band director for my whole entire career, and that's what I was going to do. And that changed very quickly, so you never know where you're going to wind up in life. I left college with a degree in music, taught for 2 years, promptly burned out and joined the Army. Was in the Army for 4, came out again and rejoined teaching again. Moved to Georgia in 2000, teaching elementary music. And along the way, I picked up more and more computer science until now, here I am today. This evening's presentation, our goal is to kind of work through some issues in what I call computational science education, or why it's important, some different elements of how it works. We'll go through 4 different online computer science systems. I'll give you a demo of each one. And at the end, we'll have some time for questions and answers. Hopefully you all see the presentation on your screens.
Yes.
Are you all muted? Yeah, okay. So just kind of give me a thumbs up there. On the chat end of the GoToMeeting, I put a link to this presentation on. If you open up chat, so you can follow along with that, have it for your records. So there's a link there just for you. So computational science education. So you know, when I started working with students in computer science as a music teacher, I really started working with the broadcast studio. So I had these students from my drama club who gave the morning broadcast, and I had to teach them how to use PowerPoint and Word, and this was back in 2005, 2006. And along the way, we wanted to have something more, so I started teaching them some programming. And then as part of developing a curriculum for technology, I sort of identified these 8 areas that you see on your screen, starting with they're hierarchicals. The simplest one being the passive perception, moving all the way up to what I would consider the highest level, which would be hardware creation. Passive perception being that, you know, you put the students in front of the computer and you say, watch this video, or you show a YouTube video to the class. The next level, being active research, is when the student is sitting at the computer and they're taking themselves through a path at specific points in content. That's like surfing the internet, if you will. The next, number 3, is interactive one-way, and that's kind of like the skill and drill, where somebody in the outside has come up with a program for the student to do. The student works through the drill. The 4th is your communication and expression, and that is your user, your student, is creating content with the computer in some way, be it verbal, text, images, writing a story, putting something on the web. Number 5 is really where we're here today. You know, when I came up with this list 8 years ago, we didn't have Twitter or Facebook or Pinterest or Instagram or any of the ways that students communicate. So really now today, students have gotten much more use out of number 5, this two-way interactive creation. And really in a lot of school situations, it's been my observation that we are really good about teaching the students through levels 1 through 5. Today we hear a lot of this talk about STEM education. I'll write it up here. STEM, science, technology, engineering, and math. This in the last 3 years has exploded upon school systems, particularly like the independent school systems for now are clamoring for STEM teachers and STEM technology. I work for Marist, and they just got a grant, a fairly large grant to hire a STEM coordinator. And I just found it fascinating that now with this interest in STEM right now, this is where we're going into kind of our 6, 7, and 8, where you've got data manipulation and analysis, software creation and programming, and finally hardware creation, which is like robotics. I found it interesting and fascinating that my father was an industrial arts teacher, and what we used to call shop is really working its way back into education today. So whenever you'll hear the word STEM and STEAM thrown around as you move through your education, but that is really kind of what I'm talking about here. And really my goal as a teacher is to have my students live in the world of 7 and 8. And I saw this as a need 7 or 8 years ago when I started, and really now today is kind of what we're talking about tonight, is that students are encoding their logical thought and algorithms into the computer, the students using the computer, telling the computer what to do. And finally, in hardware creation, the students designing and assembling the actual hardware to run and to do the software. They work with number 7. Along the way, as we're going tonight, if you have any questions, if you want to type them in the chat, that would be wonderful. I'd love to have feedback during the class. So it's a little weird to talk into the air. So feel free to chat or you know, just throw questions out. It's kind of help me direct the talk as we go. Why is computational science important? And it really comes down to, you know, in school, we teach reading and writing in order to really teach students how to think. Through writing, they can put their thoughts down on paper. They can read their thoughts back to themselves and refine them. And math allows us to model the world through number systems and operations. And finally, arts allow us to encode our nonverbal thoughts into a dynamic system that changes over time. Well, where computational science comes in is it pulls in all three. It allows humans to encode their logical and algorithmic thought in this dynamic system that changes over time. So, in teaching, the question you must always be ready to answer is, why is my subject important? Whether you're math or speech pathology or music or reading or computer science, that's a question you have to be ready to answer. For me, in teaching computer science, this is the answer here, is that computer science sits in this unique space between the arts and between math, using the tools of reading and writing. So in a way, computational science combines writing, math, and the arts. Computational science employs the act of writing with a language of mathematics and in a dynamic and changing system like music in order to create algorithms to solve problems and engage in self-expression. Okay, now the word computer science is typically used, and recently I've started using the word computational science because really computer science puts too much focus on the machine that we use. And you say computer, and of course we picture a screen, a keyboard, maybe a touch screen, maybe a mouse. If we talk to our students, they are much more attuned to using their mobile devices, their phones, or other in smart devices around them. So I like the term computational science because that embodies the human activity of design, of analyzing, designing, implementing, and testing hardware and software systems. So as teachers, our job is to teach human beings how to be better humans, and through that, one of the ways they can be better humans is to learn the art of computational science. All right, so that was kind of the philosophy. That was the why we do computer science. And now we have some kind of the goals of CS activities for the classroom teacher. And this would be for a teacher that maybe does not have a background in computer science. You don't have to have a background in computer science to teach computer science. I started as a music teacher. I started with a passion for drama and for telling stories and for working with students. And then from there it worked into robotics and built into what I do today. So part of the goal of this presentation here is to set out some activities. So really when you're teaching computer science in a classroom, you come down to three general areas. The first one is what we a computer science person. What does it mean to teach computer science? This is the answer that they're going to give you, and that's algorithmic solving or algorithmic problem solving. And that means you're building a series of steps to have the computer or the system follow. And what these series of steps do is they solve some type of problem. If you talk to a computer scientist, this is the classic definition that they will give you. And in fact, when I first started teaching computer science and first started doing workshops, I would get some very vigorous discussions with people who majored in computer science because they would sometimes look at what I did in this creative area, and they were programming, or that's not computer science. And it was really only recently, in the last couple of years, when I started teaching high school and really sitting down and talking with a computer science teacher to kind of build this difference. So that's one of your activities. My favorite one is the second, and that's creative and interactive expression. So that's when students, they create their own problems to solve. So they're writing a program or building a robot or doing something in order to share some type of idea or some type of expression that they would have, be it an invention or tell a story or like that. And finally, the third area, and this is probably most accessible to classroom teachers, is using computer science type skills for communication and content delivery. Instead of having a student create a PowerPoint about the subject that you're teaching, have them instead write an animation from scratch or build the device that demonstrates it. So those are your goals for activities for the computer science teacher. Oh, okay, I have a question at 8:10. I'm going to stop and answer this. Thank you so much for asking questions. The hierarchy, that's a great question. The hierarchy that I mentioned in the beginning. This is based on, I'll write it here on the slide, Edwin Gordon. He wrote a book called, oh my gosh, it's called Music Learning Theory. That's the name of the book, Music Learning Theory. And in Music Learning Theory, Gordon described this process called audiation. And the process of audiation was the ability to hear and imagine music in your mind. And then Edwin Gordon identified 7 different stages of audiation, going from simply listening to music up through being able to write and compose music yourself. So this Edwin Gordon learning theory of music is what I've been really seeking to apply in teaching computer science through the years. So I hope that, who asked that question? Kim Hewitt, to the entire audience. I guess that was Dr. Hewitt. So that's kind of where that came out of. This was based on Edwin Gordon's steps of audiation. If you looked up his steps of audiation, you would see they're kind of closely parallel this idea here, except he's dealing specifically with music. The switch for me, Sarah asked everybody, why did I switch, I guess, from music to computer science? It was sort of an evolution. I started as a music teacher, but I paid my way through college doing computing, writing code, doing some electronic typesetting. So technology has been in my life. In the mid-90s is when computer animation started coming to the front, and I watched my first episodes of particularly VeggieTales, for lack of just little computer videos. That really struck me as someone who taught drama, that just as a great tool for storytelling, and that led me farther and farther into the world. Recently, actually, I may have started really moving the switch in 2008, which is when the economy started to turn. And as a music teacher, I wanted to get into a field of teaching something outside of music, perhaps to make myself more marketable. But really what mostly led me into that was that I saw students using computers, but not creating with them. And anybody can use a computer, but it takes a special person to create. So really out of my mission in teaching music, which was to teach people to be able to make music, that evolved into teaching people how to make with computers. So that's one of the reasons why I led to the switch. So we haven't left, you're welcome. So back on some goals and activities for the CS teacher. So we had these 3, algorithmic solving, creative and interactive expression, and communication and content delivery. In that, our next slide here describes, okay, what are some software system goals for computer science education with younger students? And for the purpose of what we're talking about here, I'm talking with probably 2nd grade through maybe 6th grade students. I'll address some high school ideas later. And some of our goals, if you're a teacher and you've got a group of students in front of you and access to computing devices, these 5 are really the requirements that that I use to pick the softwares to demonstrate for you tonight. The first one is that it is web-based. There should be software that the student accesses through the internet. It used to be you would have to install software on computers, and if you're working within a school system, that can be very difficult to do because of sometimes the permissions with the computer or compatibility. Today, there are so many systems that are web-based, such as the one we're using right now to communicate with each other. So the web-based is one of them here. Second is visual programming. We want to be able to have our students experience this act of programming or creating with a computer and then limit the typing or the keyboarding the students have to do. If you're talking students 2nd through 6th grade, they sometimes, a lot of times, especially 2nd through 4th, they do not have the fine motor skills yet that allow them to be expressive with typing. Students typing at this young age, often that will hold them back. The act of finding the right keys or finding the right syntax slows them down. So what we want is a visual programming system, and we're going to demonstrate to tonight. The third is object-oriented. That's a very computer sciencey term, but that means you are teaching the students having them work through a model where they are manipulating objects in the program that represent the real-world objects. That's the way software is written today. You want to have some problem-solving activities. activities that have a definite solution to them, so when a student completes the program, they feel a sense of accomplishment. And then you want to balance that with some creative exploration activities. So these are the 5 requirements we're looking for. And with those requirements in mind, we're going to talk about the systems we can use. So one of the questions that was presented to me in preparing this was how would you add computational science during the instructional day? And really 3 ways. One is to leverage your device usage already available. Do you have computers in your room? Is there a lab? Are the students allowed to bring their own devices? That's BYOD. You can set aside time for activities, computational activities within the framework of other subjects, math, science, and art. We'll have some examples tonight. And finally, and this is probably the most important one, empower your students to pursue the C activities during their non-classroom time. Because so much now is web-based, you can send the students home with a login and with a URL, and then they can do these activities at home. And many of them are designed to be quite fulfilling, so you'll find the students motivated to do these. So they don't have to have the computer during the day or at the school. So with that in mind, here are 4 online computational science teaching systems. Now we're going to look at these 4 tonight. I'm going to demonstrate each one, show you some examples of coding. Each one I'll demonstrate a little bit of making. And you might want to try along on the side as we're working through these. So our first one is, I'll go through the first 4. You've got Scratch, which is one of the first tile-based programming environments out of MIT. Scratch is primarily a creative tool. You've got code.org, which is another tile-based programming system that's devoted primarily to problem-solving exercises. You have EarSketch, which is near and dear to my heart. We created that at Georgia Tech. I got to be part of that team. And that is a music mixing system where you get to, and it's text-based programming, so you're doing some typing. The music is coming out. And finally, the 4th is Sketchpad, which again is text-based programming, and that's using Java and JavaScript, doing some graphic programming. So we'll walk through the 4 of these. So our first one is Scratch, the original. This is what got me into teaching computer science back in 2007. I remember I was beginning to switch over to, I had the kids, we were doing lots of PowerPoints. We were doing these 1,000-slide PowerPoints to do animations. And I remember seeing an email coming out of Georgia Tech saying that there was this new system called Scratch, and they had this workshop for it. So I remember coming on to Google and looking up Scratch and finding the website and downloading the program and saying, this is exactly what I've been looking for to teach my students. And it's been around for 8 years, which is an eternity in terms of computer software, but it's one of the original, and it's really still one of the best environments. So yeah, again, a description of Scratch. It was launched in 2007. It's a free block-based programming environment created by MIT to produce media and teach programming concepts. You join together, how Scratch works is you join together block icons representing code, and students create games and stories and simulations in which programmable objects called sprites move and interact. Scratch's graphic programming-based environment provides an excellent platform for teaching computer science concepts such as objects, methods, and conditional statements. Saw a question from Destiny saying, I know these programs are meant to teach children computer programming. Are they also a good place to adults to start when learning? And I would say yes. I came out of my college background with some self-taught in computer operations like networking and a little bit of electronic typesetting, but nothing in programming. And while I had tried to teach myself programming prior to 2007, really, when I started using Scratch and making Scratch for my students, that's when I really started to grasp the ideas of programming, of using variables and objects and methods. And so I think as adults, Scratch is a good place to start too. Kind of as a poll here, I guess we are talking to freshmen, sophomores, and juniors. I saw that it looked like Sydney said they used it in high school. How many of you have, I guess you can chime into the chat. How many of you have used Scratch in high school or in some way in your learning experiences? I don't know how to do online polls with this. I see Sydney said they used it to teach us in high school. So I mentioned some of you, oh, wait, there's Sarah. Graduated 2005. CS wasn't much of a focus. And that's from Sarah. One of the reasons I did change school systems from where I was in Paulding to Marist, an independent Catholic school where I am now, was that I had a hard time selling the idea of doing computer science at the high school level in terms of doing Scratch and robotics. We had teachers at the high school who were doing it in Paulding, and there were many of supported individuals, but as a music teacher, I could not find room for it in the high school. Senior year computer science class from Alexis. So yeah, so kind of a smattering of answers ranging from not doing it to doing it some in your senior year. So you know, Scratch again, very popular in school. I remember when I first started doing Scratch in 2007, 2008, 2009. Hardly anybody had heard of it. Now it's very popular. Some advantages for Scratch. It's easy and fun. It is just really fun. It's visual. It's kind of the way we think. Someone had asked earlier, you know, is it a good way for adults to learn? When you open a book and it has just pages and pages of text telling you what to type in, and you have to abstract it, it can be very difficult. But because Scratch is so visual, it matches what we do internally. Mitchell Resnick invented Scratch up at the MIT Media Lab, and he did a lot of research reaching back into the Mindstorms book and some of the logo turtle programming they did in the 60s. And all the research that went into developing a user interface that's very intuitive. Scratch is object-oriented, which matches the way computer programs are written today. It's flexible. And this is why, for me, Scratch is still one of my favorite systems. You can sit down with a room of third graders and teach them some techniques with Scratch, and they'll have a great time and they'll learn. And you can sit down with some high school seniors with Scratch and challenge them mathematically with the same program. Scratch today runs on the web. It encourages open source and sharing, and it is free. You do not have to pay for it. And as a teacher, programs that are free, resources that are free, that you take them with great gratitude. Scratch user interface. Here's an example right here. You've got a world over here on the left, which is where the program takes place. A sprite, and here's the cat, is any object or character in the program. There is a scripts pane down the center, which has these blocks that tell the object what to do. Then over here on the right, you put the blocks in, and you click play, and the object does what you tell it to. There's an online editor, because I'll show you the next slide. These slides outline some of the blocks. And I wanted to jump to some activities. I'll give you some demo of some student activities here, and then I'll give you a live demo of making something. There are really three types of activities students engage in, really, in anything. And this comes back to my music education when I learned ORF, show work, which is a way of teaching music. But children, human beings, we like to play games. We like to do simulations, and I kind of put interactive art in simulations. And we like to tell stories. So the types of Scratch activities kind of come down into these areas. A game would be, this one over here. I'm going to click on this link, see if I can bring this game up. I'm going to slide a screen over. So you've got the Scratch game right here. Let's see, hopefully you all can see this. You click play, and you use the arrow keys. The little guy moves, he swallows the dots. This is Pac-Man. When I first started teaching Scratch 7 years ago, this is a lot of what we did, which was games. This is kind of what I understood. If I click C inside, you kind of see that there's the blocks here. These are called event blocks, like when right arrow is pressed. You click that, it moves the little man, and he can swallow the dots. So that's our example of our game type program there. One of the very first examples I tend to do with students. Some simulations. When I was a music teacher, I would do activities where we would have the students create virtual instruments. So here we have the virtual xylophone. I don't know if you can hear my computer if I play it. Yeah, I'm getting some feedback here, so it's cute. Love it. You can change the instrument. So part of in learning this is learning how we can use numbers to represent different sounds. The students had to create the bars, and each bar is an object that's represented in the real world. A wooden bar that has a certain length, and when you hit it, it makes a pitch. Over here, you see the scripts, and when the 1 key is pressed, this broadcast plays. This broadcast is this command. When I receive low C, switches to costume, which is how we get the white around it, picks the instrument, plays a pitch, switches the costume back. So this program here, which is something I did with 4th and 5th graders, really taught them a lot about programming. Playing music with a keyboard, what a time to be alive. It's great. Again, this is one of my favorite activities when I was teaching music, and I still even use this with my high schoolers when we talk about object programming. You'll see here there's something called a note list, and this is where Scratch is really a very cool program. This is called an array, which is a pretty advanced idea in computer science. An array collects information in one spot, and what this array allows you to do is to record yourself. So I'm going to demo where I'm going to click the record button here. I'm going to record some music. And you'll notice as I recorded, it put each note that I played into the list. And then to play it back, click on the green triangle. It plays it back. This is how I introduced the idea of arrays both to my high school computer science students and to my elementary and middle school students. What's an application of this? If we've seen movies like Planet of the Apes or Lord of the Rings, Andy Serkis is a famous actor now who works with what's called motion capture. And if you've seen that where they put the little balls all over the suit, Andy Serkis acts out the part, they record all of his actions, and then they play them back in a computer-generated character. This note list is a one-dimensional version of that idea, where you're recording ideas, where you're recording information in a spot, and then you're playing them back. So this is one of our examples of Scratch. A third one, this is a personal favorite of mine. This one here, this project is storytelling, and we had a project where the students had to take a song.
Christopher?
Yes.
Can I interrupt you just really quickly? Is anybody else hearing a strange sound when he speaks? No? Okay. No? Okay.
Maybe
good.
That's just my voice.
No, when you began the last name xylophone project, it sort of created a feedback thing in my own microphone. Let me mute you and unmute you really quickly, or let me just try that really quickly.
Okay.
Okay? Okay. You can go on.
Do I sound better now?
I can understand you, and if they're not having any problem, and we're good. I'm going to just mute myself and let you continue.
Am I better now?
Well,
okay, I'll continue on, and if
yeah, it'll resolve, I bet.
Okay.
I can understand you, so, and they're not having a problem, so we're going to keep going.
Okay. All right, wonderful. The third project I have is, and it's also made by my daughter, so I'm a little bit prejudiced, but this is an animation she made to a song, and we're going to go ahead and play part of it. This is from the song came from a cartoon that was on a couple of years ago called Making Themes, which I thought was really clever, but it's two characters singing, and she animated this with Scratch, so I'll bring this up, and I will play it for you. My daughter, who is 15 now, would be mortified that I show her work to people. Here we go. See if this brings up. This may or may not work. I may be pushing the internet to the limit. It's not loading. I'll reload it. If this doesn't work, I'll go on. Looks like it's going to work. I'm going to set this aside and see if it loads. If it does, I'll show it to you. If not, we'll just have to trust that it was really awesome. The link is here, so you can check this out on your own. But in terms of Scratch projects, probably for a, and she was in 6th grade. Oh, here it comes. So this is the, again, this is animation with Scratch. So that's an example of animation with Scratch. So students, in fact, there's a whole, in the Scratch, which has an online website, their whole community is the students who engage in these kind of animation. On to some interdisciplinary uses for Scratch. When I was teaching 4th and 5th grade, and really, when I was teaching music, I was a K-5 music teacher, and I had a great principal, and she agreed to let me do computer science for 3rd, 4th, and 5th grade, and then K1 and 2 I taught music. So the types of, I would consult with the classroom teachers, find out what they were teaching in the core curriculum, and this was back 2010, 2011. I can't even remember. Oh, I'm just catching somebody from a comment here from Sarah saying that I worked for 3 hours on a 3-second Scratch barely moved. Kids can learn so much if they're given a chance when they're young. Yeah, students can do amazing things. So for the 5th graders, they studied states of matter. And so what the students would do when they came to me is they would have to use Scratch and make a simulation to show the movement of the molecules based upon the temperature. So I had a link I used with the students, and so these are the references to the M5, P4. These were the Georgia Learning Standards, and they might have changed in the last couple of years. But the idea was that the students had to make this project. I had some directions for students, some broad directions, and then I also had some detailed step-by-step directions I would have available for the students to do. I kind of walked them through it, through the activity. I found with younger students it was really important to give some very specific directions at the beginning. It helped them not have the kind of frustration. The finished project looks something like this. I'll go ahead and bring up the see the inside here. You can see on the Scratch website, when you create a project, it's shared. So what you have here, you have the variables, which are in computing, that's ways that you can store information. We're storing temperature and the number of molecules and then the size. So when I click play, 31 molecules are going to show up. I can control their size for viewing by sliding the slider. And then the students would have to put this temperature bar in, that would temperature variable, that's the higher the temperature would go, the faster the little molecules will move. And if the temperature was 0, the molecules would almost come to a stop. Now, this was not a super realistic representation of the quantum activity of molecules, but for 5th graders who are still concrete learners for the most part, this would help to give them the idea of what molecules were doing, and it gave them a way to express it. And a lot of times they would have a great time designing the actual molecule sprite itself. I'll use 5 here, so there's less. So that they would draw all kinds of crazy pictures of the molecules. I would often start this lesson using dry ice. I'd bring a bowl of dry ice, and we would play around with dry ice, and then after we talked about solid, liquid, and gas, then we would make the project. Another example for 4th grade science was the planets. The students would study the planets. And again, a difficult challenge for students is visualizing the movements of planets through space. They can study the phases of the moon, but for them to actually make it and see it is another skill. So my students in 4th grade would create something like this, where they had to create planets like the Earth or Mercury. And the goal is that the inner planets had to spin faster than the outer planets. And to really challenge the students, we would say, okay, make a moon that can orbit around the Earth. So I hope you all can see this here, but you've got the Earth and the moon, the Sun, the fast Mercury. And then once they make the projects, often I would let them play around a bit with them. So if I add a clear and a pen down on these objects, and clear, pen down, oops, pen down, and then go to the moon. This is really cool. Clear and pen down. When you run the program, you see the paths drawn out by the objects. And it's really cool to study either the slightly elliptical path or the perigee. The pattern the moon makes as it's going around the Earth makes a really neat pattern. And again, this is kind of where we're crossing art and science together, and the students were fascinated by this, and we could watch this for hours. So I'll take it off the screen so we're not distracted. There we go. Oops, this page. So that was one of our examples. The Amplitude project was another 4th grade example. Students studied sound and waves. So again, along the similar vein, I'm going to say allow. Scratch can read your microphone, and if this is working, this might be because I'm using mic sound with this. In fact, maybe you don't hear me anymore. But when you're just up, now it's listening to me. So it reacts to the amplitude of the voice, and I can change the frequency by moving this. So again, the students would follow the directions and create these kind of activities. And hopefully my voice didn't drop out there when I turned that on. So again, some interdisciplinary projects. Math was the Polygon project. This exists in other forms on other sites. I'll demonstrate this really quick. Let's see, time is running. Oops. Polygon project, again, they're manipulating the size of the polygons that are being drawn, how many sides the polygon's drawing. The more sides, the more it approaches a circle. There's the concept of limits there. The turn and the arc and even the pen size. So again, this big object of computer science with younger students is let them realize that you create these boxes called variables that can hold information, and as you change information, it changes the output of the activity. And along the way, we get to do a lot of algebra to figure out the number of sides in an arc. So there's some multidisciplinary usage. And music, I showed you the xylophone project. So that's one example. This slide has some links for Scratch. These are some lessons that I've made up, and also some links to some resources from MIT. So that is Scratch, I believe. It's a celestial spirograph. I can't wait to show this to my kid. Yes, the spirograph is doing that. We've been doing that for years, and once the students make it, they are all so fascinated by that, and it's just really awesome to watch it when they have control of their own spirograph. Moving into the second, I'm going to move through the next three here. We've got code.org. Code.org was launched in 2013, and it's dedicated to expanding participation in computer science by providing free web-based lessons and activities. And Code.org also strives to provide a balance in activities geared for both boys and girls. Scratch was great. It provided this great platform. But one of the challenges of Scratch for teachers is that you had to come up with the activities for the students to do. And sometimes in creating these open-ended projects, unless you created rubrics or some type of grading system, sometimes the students wouldn't know how well they're doing. So code.org is kind of the answer to that. And code.org, in many ways, is based on Scratch. Code.org's main focus is problem solving. And the scale is really designed for pre-readers to late elementary. In pre-readers, they work on mouse skills and they workflow in a tile-based environment. And I'm going to show you this because it's just really cute. It's these little beginning lessons for kids who are in first and second grade, which they didn't have this when I was teaching elementary. So you've got a course 1, there's like a little studio. I'm going to start with stage 3, which is learn to drag and drop. And keep in mind, this is now we're talking about first and second graders. So you start on stage, kid clicks on stage 1, and it says, there's a little video telling you how to do it. Click OK, and here's our first program. You drag the smiley over there. Yay, you've completed the problem. And then you move through, and it tells you, okay, what you do next. And the whole purpose of these early lessons is to teach the students the mouse and visual skills they need for tile programming. My wife caught me doing this one afternoon, and she thought I was crazy. Because I alternate my time between doing master's coursework at Georgia Tech, where I'm really doing all these crazy algorithms, to putting elephants together. But you can see by the time you get to the end of the sequence, now what you're doing is you're starting to work with these structures that are more like the programming blocks. So the students have to match, and if you're colorblind, you're kind of out of luck here, but they have to match the sequence of colors. And this is for your pre-readers. So while it's not, I would argue maybe this isn't computer science exactly, but it is teaching the students the kind of mouse skills that they need in order to solve these problems. This comes from very simple. I guess I need to find a more complex one here. So let me back up to, I'm going to do the frozen activity here. So again, this is designed for, you're running a class, and here you're dragging, okay, move Elsa forward by 100 steps. You click the right, and forward, you solve the puzzle. At the end of the sequence, now you have to make Elsa do this kind of snowflake here by walking. So again, you've got have more commands. You've got create a snowflake branch, which is like a function. So it can quickly get more complicated. But again, this type of activity, while it is Scratch-like, it's very focused on problem solving. You are giving the students some kind of model, some type of solution that they have to produce by choosing the code, which is different than being creative. So that's one focus of code.org. They do have some artist activities. So with the artist activities in code.org, they are very similar. In fact, they're almost exactly like the Polygon project. You're drawing a square, move forward, turn right, repeat this a bunch of times. It says I did it wrong. And it's very interesting is that I take probably unnecessary pride. I was doing this kind of activities with my students 5-6 years ago, and it's really neat to see them now coming about in code.org. At the 10th level, I think what they do is they're asking you to be very creative with it. So there is a creative sense to the code.org, not as open-ended as Scratch. They also have a play lab where you are working with characters. Oops. Put it on my other screen. I'm going to jump to level 10 here. And at level 10, you're kind of creating your own animation by deciding which actors, choosing certain images for actors, and click around, puts my unicorn on the screen. So there is giving some room for creativity here in the code.org. Not as open as Scratch's, but very, very accessible. Some of your advantages to code.org are that it is absolutely teacher-proof. It is totally self-directed. Once you guide the students through setting up their accounts, they can be implemented with little training on behalf of the teacher. Okay. I had a question. What age would you suggest the early learner exercises for? These did not exist when I was an elementary teacher. I would say they're appropriate through K through first grade in terms of getting the students, teaching them math skills. When I taught kindergarten, when they came into my class, I did music mostly with them because pedagogically, students K through about third grade, they need to spend most of their day moving and learning but with their hands, not sitting in front of a screen. But if I had to sit them in front of the screen, those kind of activities, the early learners would be for the little ones, K through 2. Code.org is pedagogically appropriate for your pre-typing students. Focuses on movement in 2D space, and it teaches kind of your shapes and colors. And it's web-based and free. Your disadvantage of your code.org is that it doesn't support variables and other structures that computer science teachers really want students to learn. You're unable to import your own graphics or sound in code.org. In Scratch, and I didn't demonstrate this, let me bring up I'll try and talk and bring up a Scratch editor at the same time. In Scratch, you can import your own characters and actors. I'm going to make a blank Scratch project here. In Scratch, when you are presented with the screen, if you want to draw your own sprite, you can click the little paintbrush, and then using these tools over here, you can draw out really anything that you would like. This is my very bad drawing here. But you could make this into a sprite and put it in your world. In Scratch, you can also record your own sounds. Hello, this is Mr. Michaud. And then you can edit them, you can reverse them, you can do all kinds of crazy things with them, crazy effects with the sound. So Scratch is much more open in terms of what it can do. Code.org is a lot more closed, primarily, again, because it is focused on problem solving. This is a philosophical aspect of my part. Code.org teaches students that coding, and I'm going to really emphasize this here, because this is where I probably disagree as an artist with other computer science teachers. The process of coding is seen primarily as a means to solve other people's problems and not create your own work or expression. And this is key. This is a key philosophical point. There are times when you teach students the tools so they can solve problems, think of word problems, but there are other times when we teach students tools so they can create and make. And in teaching computational science, you really need to balance both. And that's where I think code.org kind of falls short. And that's why in my own teaching I don't use code.org a lot. I defer back to Scratch. So as a summary, code.org is appropriate for first experience and tile-based. It's useful for students younger than 8 years. You'll need a plan if you're working with students older than 10. Either something with Scratch or something, probably something that kids who will go through really quick so they don't get bored. And you got to balance code.org with expressive and communicating activities. All right, I got about 5 minutes left. So I want to demonstrate these last two. These are not tile-based. These are text-based programming. First one I want to talk about is EarSketch. EarSketch is launched in 2012, and it's a programming environment based in Python, and it's really based on music making. So someone had asked, like, how do I really learn programming? EarSketch is one of the ways. I'm going to bring up the site. Let's see, here's the EarSketch website. There's a whole curriculum built with EarSketch. I'm going to show you the online editor. So you type some code down here on the editor. You click Run, and it shows up here. I'm going to load an example that I've already written. So you can see there's some. So let's pick a different one. Let's do the A/B demo instead. So you call some commands like fit media, pick some music, puts it on the track in a loop. I'm going to run it, and it inserts the music, and then you click play, and you rock out. It's so much fun. This EarSketch environment is more appropriate with high school students. In fact, it's so much fun, I want to show you another one. Actually, I'll show you how to make one from scratch here. I'm going to do a new script. So there's a list of sounds over here. Yes, EarSketch is web-based, and it is, again, this is kind of meant to be kind of the text version of Scratch. It's based a lot on the idea of Scratch, except it's text-based. So I'm going to choose a sound. So I'm going to go over here to, not Young Guru, I'm going to go to Richard Devine. I'm going to go to techno because I was born in the 80s and everything is techno. Go to main loop. So here's a beat. So let's say I wanted that beat. It's kind of like GarageBand. I can go down to the code area. Let me make the font size larger. I can type fit media. So I want this sound, so I'm going to click paste. I want it to be on track 1 and go from measure 1 to measure 9. And then when I click run, it puts the code there, or puts the music. I want another sound. Type another one. Put this on 2 from 1 to 9. I can run, and it will live put the sound back in. So now if I wanted to put some music in there, I'm going to say fit media. And put my club lead in on track 3 from measures 1 to 9. Run it. And now I'm a DJ. I'm mixing sounds together. EarSketch is relatively new, but we've had great success with it at Georgia Tech. I was part of the group that actually designed it. Some of those commands, I actually got to write the coding behind them. It was very exciting. It's Python and web-based. It's founded through the National Science Foundation, and the whole curriculum is on the website. In these slides, I included a lot of slides showing how it works. So feel free to jump on board the internet and start exploring. There is a section on my website called EarSketch. And some advantages of EarSketch is it's Python-based. It uses a real programming language that transfers to what we use in universities and industry. For older students, for middle schoolers and high schoolers, it feels more authentic. It's for students who are not interested in graphics and games. It's a way to reach them, like the band nerds, as somebody had mentioned, and it's supported by an extensive online curriculum. So that and that is EarSketch. I teach, I teach now in an independent school, and the students at the school, they had zero interest in Scratch because to them it seemed like a toy, like a game. But when I do EarSketch or this next environment, the processing, when I use Java and Python, they get just as excited about it. Some disadvantage, and music comes with a lot of baggage. Some students have strong musical tastes, and you got to get around that. You have to be able to type and read to do EarSketch, and you have to have attention to detail. It's a little bit difficult with your own musical clips, and sometimes bandwidth issues in a lab can be sometimes in a public school or in any school situations where you have a lot of people on the internet at the same time. It can be difficult. Finally, processing is the last one. I'll mention this one briefly. It's kind of like Scratch, but instead of typing, instead of dragging and dropping, you are typing. So this is Sketchpad CC. This is also web-based. I'll bring it up here. So what you do with Sketchpad is you can, so notice a little bit like Scratch. I can click play, make some pretty pictures here. And then you can look at the code, click View Source, and there's the code there that you can type it in. So I've got a number of lessons on this on my website. Again, this is good for the older students, for students who've done a lot with Scratch, have kind of worked through Scratch for a couple of years. When they're ready for real programming, if you will, I will use Sketchpad. This is what I use now primarily, processing EarSketch with my students in 7th through 12th grade. And I believe that takes us to 9 o'clock. Let me make sure I didn't leave anything off the PowerPoint here. Everything that I've talked about tonight is free, which is great because you can create these free accounts. So let me move to the end. Question and answer time. So thank you so much for letting me talk to you all tonight. Wish I could meet you live. Are there any questions that you might have? trying to think if there's anything else that I might have missed.
Can you tell me a little bit more about processing? That last one
Sure.
Is processing, is Sketchpad one of its tools, or is it called Processing Sketchpad? Is that what it is?
Oh, okay. Thank you. So what processing is an install program. I'm going to go ahead and start it right now.
Yeah.
And I'll bring up, actually I'll bring up some projects here. So processing is a program that you install on your computer. It was made at MIT, kind of like similar to Scratch, the idea that you could give non-programmers, artists, a way to express themselves. Let me find something here, something that's interesting to look at. Let's see. So, expect the token. It is text-based. It looks like. I was teaching with this last week. Let me delete this out and see if it runs here. Waiting for it to run. There we go. So this is actually not particularly interesting, but it's a way that you could make graphic programs by typing. So you define classes. Like we have sprites and actors. I have the students create their own sprite, and we call it actor. And then they can create subclasses. And I wish I had set aside a more interesting example. Oh, you know what? I know what I can do. Give me a moment. I think I can find.
Is this based on a language like Python?
Thank you for asking. It is based on Java. It is
okay.
Based on Java. So again, kind of like EarSketch. It's based on an actual language.
Mm-hmm.
And I've got more notes in the PowerPoint, but
okay.
There it is. Here's the sample. So this is one of my eighth graders made last year. So this was the project. So they had it's in a way of creating art. So she had to type in the code to make the triangles, to make the lines, and then she found some particle simulation code online, and she had to adapt that to do her project. So we do about a 3-week unit with processing. Sketchpad.
Thank you.
Sketchpad is an online version of it. So it's a web-based, because I wanted to focus mostly on web-based programs tonight, that's why I chose to use Sketchpad instead.
Okay. Thank you.
Okay, so let's see. Sounds a long question here. I have a question that is personal interest to me. Don't completely answer. I looked in the website and saw that academic rigorous Catholic school. Together, rise of technology has caused a major decrease in religious affiliation. Huh. That is an awesome question. Do you mind if I answer that?
Please do.
Yes. You know, one of the reasons I chose to work at Marist was because of their religious mission, and I'm going to, which is to form the whole person in the image of Christ. And I'm not a Catholic myself. However, the way I approach and look at programming, when we engage in the act of creating, we are joining in the heritage that has been given to us. And I'm not going to preach, but I am going to say this, that I always tell all my computer science students who feel that they feel a decrease in their religious interest. We go to Genesis and we read those opening chapters when God created the heavens and earth. He created light and he separated light into darkness, and he created the land and the sea. He created the sky, and that's very much like defining classes in Java. You define what a class is, you define its properties, you define its methods. So we kind of look at our Lord as the master programmer, if you will. So I see that there is, as students get in, as they feel like they are more intelligent, sometimes they feel less a need for spirituality in their lives, and that's kind of one of our goals at the school is to mitigate against that. I hope that answers the question. The Marist is an interesting institution because it is a Catholic school. It is also a rigorous college preparatory school, so we sort of live with a foot in both of those worlds. Destiny asked, so once the kids, even ourselves, master these programs, what can we as teachers do to challenge them, help strengthen their CS skills? If you've got students who are really, really getting into programming, there's a site, I'll type it here, it's called Coding Bats. Let me double check the URL on another page, make sure I have it right. codingbat.com. There we go. codingbat.com. I'll put this in the tab here. This is from org HTTP. This is very similar to code.org, except it's for high school, except it's for high school students. So that is one. One means there are so much online available. You can go to Udacity or the Khan Academy. I've had students take themselves through Khan Academy to work on their CS skills. There's another website. I will pull the link in a moment. Let me pull to my one of my classes. My subplans are a site called Code Academy. There we go. Or Code Academy, which is another great, I'll put it right here. It's another great sort of self-directed site for students to work through CS skills. Okay.
Deanna asked a question at the very top of the long question Sarah asked.
Okay.
I'll see if I can find it, if you can't see it.
Oh, I see. Is it free?
She said, what would you recommend for beginning CS with 6th graders?
Oh, okay. I saw that. Okay. Deanna, right? Deanna Bird?
Yes.
All right. Hey, Deanna. Thank you so much for being with us tonight. Beginning CS with 6th graders, I would recommend starting with Scratch. And there are several websites with some really good Scratch lessons. The ICE Distance Learning, let me look that up real quick. It's the Georgia Tech website. And I'm going to paste this into the window here. Okay, they have some really good online lessons for Scratch. Also, my website, nevomusic.net /scratch.html. Oops. That has lessons I've used with 4th, 5th, and 6th graders pretty successfully through the years. And double check that URL to make sure I put the right one down. Yeah. So I would definitely, with 6th graders, start with Scratch. If you have 6th graders who are very good at typing, something like processing or the Khan Academy or even EarSketch, you would have great success with it. I piloted EarSketch with my 5th graders at first, and I find really middle schoolers really like EarSketch, almost more than high schoolers do. High schoolers, once they get a lot of experience in music and music producing, sometimes EarSketch seems limiting to them. Is that helpful, Deanna? Good, I see you shaking. This is Sarah. Oh, wait, I answered that already. Awesome, thanks. All right. Okay.
I kind of have a question for you.
Okay.
I'll try not to bog down. I've had some experience teaching a little bit of Scratch over the past 5 months, and I find that I'm challenged. I have a real challenge between trying to achieve this like ideal of open-ended and exploratory, and yet I feel like I lose people if they miss a single step. If they don't know how to do something, then you really can't be that open-ended. It feels like you have to really be step by step. But then being step by step and giving them this like recipe for what they need to make, also it feels like that's not the right spirit of the thing. So I have this like challenge, I feel this pedagogical challenge, this internal conflict between making a Scratch lesson open-ended versus prescribed, and I just struggle with that, and I just was wondering if you had any thoughts about that. Because I see you have lots of prescribed stuff, but you also mentioned, and I'm sure you encourage exploration. You said that you did in your presentation, and I know that you do, but I know that I struggle with balancing those two things.
There are a couple approaches to that, and that is a big philosophical, I still fight with this to today. Younger students especially like to know when they're finished. And if you give them an open-ended project and they run into a conceptual wall, they'll ask you a question, Mr. Michaud, how do I make 14 levels of my game and gravity so when it lands, these things that you cannot answer because they don't have the physics for it yet. So I approach it a number of ways. Number one, I encourage my students that my directions are only meant to be a starting point. So in terms of grading or rubrics, I expect them to take the project and change it in some way. For some students, adding different sprites but keeping the same underlying code works for them. For other students, they treat it as a launching off point. So that's one aspect of it. Something in I took a software engineering course last term as part of my master's work at Georgia Tech, and it was so informative in the design process. Where you analyze the problem, and then you create a design, you implement, and you test. And sometimes in our zeal to get students interested in computer science, we forget to teach good design techniques with them. So in terms of our open-endedness with them, I will sometimes take the student, and I found some success with this with processing, have them make a written plan for what they need. I may have them do a drawing. Here's the characters I have. All right, now I'm going to make a list on paper of what each actor needs to do. And they make up this paper design first, and then we can create a list. Okay, in order to do this, you have to do collision detection. So you're going to have to look that up to figure out how you're going to do that. In order to keep score, you're going to have to learn variables. Well, here's a lesson that talks about variables. Adapt that to yours. And then have them make a plan and a list of what they have to learn in order to get these really open-ended ideas. As what frustrates students about open-ended ideas, again, is when their goals outstrip their conceptual ability of where they are developmentally, particularly with younger students, and then what they see in game. Like, they want to make Flappy Bird. It's like, well, all right, how do you explain to a sixth grader linear acceleration? When the bird's when you stop clicking the bird, it falls according to gravity. So I approach it that way. And finally, I kind of look back to my Edwin Gordon, which I mentioned in the beginning, and he had this idea of audiation, where yes, sometimes you spoon feed the kids a lot of rote learning, and then they start to make the connections between these nodes. Okay, I know how to keep score. Okay, I can apply that somewhere else. I know how to make things fall. Okay, I can apply that somewhere else. And once these students have enough of these critical nodes, then encourage them to start connecting the dots. I think that is one of I think the biggest challenge we have in computer science right now. It's really easy to give the kids either recipes and have them follow them, or to put them on sites like code.org where they solve problems and feel good about themselves so they don't make anything. I hope that was helpful. Those are some techniques I found useful.
That is helpful just to hear you. I can tell you understand what I'm talking about. Yeah. Thank you.
Physical education. This is Diana. What's great about physical education, because in many ways PE embodies this idea of programming. Because when you play a game in physical education, you are programming each individual student to be an agent in the game. So in computer science, group the students up and have them make rules for their own game and have them treat each other as sprites. If you ever had them in the lab or showed them Scratch, have them making up rules to play a game, to how to score, to how to win. That is key to writing computer programs. So that's how I would incorporate it, in at least in physical education. In health, any kind of simulations or even presentations about different topics in health would work as well. Scratch is a great tool for presenting, like the storytelling, sing-song part of it. You could use that similar to the way you use PowerPoint in health to talk about some of the concepts we have in nutrition or body systems. See if I missed anything else.
I know we're at about time. I had a quick question. When you have students working on these big open-ended projects that may last for a period of time, how do you encourage them to keep track of where they left off? Do you have them sort of, do it on paper, where they kind of write a little note to self, here's where I ended up today, and next time I work on this project I want to make sure I do X, Y, and Z, or how do they keep track of their projects? Is there a strategy you use?
Let me think of that, because it depends on the class. In some long-term projects, I have what I call deliverables due. So they might submit a written plan on one day, like my app design class. They have to do a written the written plan, the drawings, the UML, the diagrams, and then the code, and then the testing. For younger students, having them leave notes themselves with comments are useful. And sometimes as part of the rubric for the project, you can have pieces of the rubric due on certain dates. Okay, you need to design the graphic look of your program. You need to draw the sprites. That's one day. Next day, I was like, okay, you're going to design how they're going to move and interact with the user. Topics like that. My open-ended projects, I try not to have them go much past maybe 3 to 4 classroom hours of work, because we are dealing with students and I don't want to lose their attention span. So I try and design projects that can be that maybe are built around a theme like the xylophone or virtual instrument or the planets. But once they've moved, it can be done within. I remember when I was teaching elementary music. Usually I saw them once a week. So typically 2 to 3 weeks with 1 period of introduction and then 2 periods of giving them time to work on it. And that would be the total for any given.
Like a 45-minute period?
A 45-minute period. Mm-hmm.
Yeah, okay. Okay, thank you. Does anybody else have any more questions for Mr. Michaud tonight? I think some people were messaging you privately, so I couldn't see. No?
No.
Well, we thank you. Your presentation was awesome. I'm sorry you weren't able to go through all of it, but you gave us a great resource that we can look at. I'll probably pester you through email.
Okay.
Maybe
Great.
later this week.
Yeah.
I actually want to run my Scratch lesson by you and see what you think about it. See if you have any tips for making it better.
Oh, great. Sure.
If you don't mind.
Okay.
But
All right.
thank you so much.
All right. Well, have a great evening.
All right. Okay, everybody, I'm going to stop the recording, and I'll stay on for a couple of minutes. If anybody has any questions, I'll stay until 9:20 maybe. If you have any questions for me or further yeah, I'll leave it at that. Thank you.